This week we're talking about information. Certainly we want to extract information from a data set, but we're going to say rigorously what we mean by the word information. We're going to start out, however, with probability, but ultimately the real goal is still going to be information. So let's go back to the clustering coefficient. We probably understand the average shortest path length, but the clustering coefficient may seem ad hoc, and in a lot of ways it really is. There'll be other measurements that we take that are seemingly ad hoc, rather than implied by some kind of geometry. However, we can think in terms of probabilities. So for instance, the clustering coefficient of a graph is between 0 and 1, so we'll just say, well, it's a probability of something maybe. Now, this certainly works for the clustering coefficient of a vertex, because it's essentially the probability that neighbors of V are themselves neighbors to each other. Let's look at an example. So we looked at this last time with the clustering coefficient of this V is 2 triangles actual over 6 possible. So that's 33%. And we can interpret this as the probability that a pair of neighbors chosen at random are adjacent. So a 33% chance. 1 out of 3 chance. But the clustering coefficient of an entire graph is an average over the clustering coefficient of the vertices. That would mean we have to talk about something like average probability. And that really doesn't make sense. So let's go back and look at this idea of measurements that are created for a purpose. In particular, we often call those scores. They tend to be defined by logarithms. You might be thinking, why? They tend to be defined by averages. Why would you average logarithms? And the key issue is that scoring is related to the concept of information. Logarithms or logs, we're going to motivate those, and we're going to motivate the idea that information is averages of logs of probabilities. And so we'll begin naturally with probability. So when you have a random process, the first thing we'll talk about is all possible outcomes of that process, and we call that the sample space. For now, we're only going to consider finite sample spaces. So the single coin toss would have a sample space of either heads or tails. 6-sided die has 6 possible outcomes. An event is a subset of the sample space. So in the coin flipping, the set heads is the event of getting a heads while flipping a coin. For rolling a die, the set 2, 4, 6 is the event of rolling an even number. And we'll simply say the probability of an event A occurring is probability of A. Now we can interpret and define the probability of an event in many different ways. As a limit of relative frequencies. We looked at that at the end of the first lecture. As the likelihood of the event A occurring. As a concept related to information, which is going to be our focus, by the way. The key thing to remember is there are many different interpretations, but they don't change basic results. So if you toss a fair coin, probability of heads is a half. Probability in the roll of a fair die of a 1 is a 6, and of an even is a half. It really doesn't matter which interpretation you use. If you have a sample space of a process, that's a set of all possible outcomes, you can associate a variable. And a variable associated with a process or associated with a sample space means that in any trial of the process, the value of that variable is in the sample space. A lot of times we call these random variables. A variable associated with a random process is called a random variable. It's still just a variable, however. So when we say X is associated with the sample space of heads or tails, then the value of x is either heads or tails. We could say x is associated with 0, 1, which means x is 1 or x is 0. So a random variable is just a variable, just like we studied in high school algebra. The word random in the phrase random variable simply means that the variable x in question obtains its values at random. Often we index the outcomes in our sample space, and then we say the probability of the random variable x being equal to some outcome O indexed by j. We can write it in several different ways. For example, toss of a fair coin, heads or tails, we might call that outcome 0 and outcome 1. And then we might write probability that x is heads is probability that x is outcome 1, or just the probability that x is 1, or the probability p sub 1, and it's a half, and no matter how you write it. Now if we have an x associated with a set, then the probability is non-negative for all outcomes. The sum of the probabilities is equal to 1, or in our subscript notation we would write p sub 1 summed up to p sub m is equal to 1. We often use x instead of j as an index. So we have capital X as the variable and then little x as the index. So instead of writing O sub j, we might write O sub x. And the probability that x is outcome O sub x we'll often write as just p of x. So p of 1 up through p of m is equal to 1 would be our law of the sum for the sum of the probabilities. We often have more than one variable. For instance, if we roll 2 dice simultaneously, then we'd have x be the outcome of the first and y would be the outcome of the second. If we had a square on a chessboard, we might choose that square at random from row x and column y. If we draw 2 cards from a deck, x is the result of the first, y the second. First and last names of a person selected random. X is the first, y is the second. So we have to modify our notation, but in essence it just means we're using 2 indices, and therefore we have an I and a j, and we would write the probability for both variables. So the probability x is I and y is j is the probability that outcome OIJ occurs. And similarly, we often use lowercase x and y as the indices. So the probability that capital X is equal to the index little x and capital Y is the index little y, that's just a way of saying the probability that outcome O sub xy occurs. So let's just look at an example for the notation. So suppose we had 100 students randomly allotted among 4 teachers. A trial for this experiment would be a student and teacher selected at random. X will be the student and Y will be the teacher. So M sub X will be 100, that's the number of outcomes for X, and M sub Y is 4 because there are 4 teachers. So X ranges from 1 to 100 and Y ranges from 1 to 4. The sample space is the doubly indexed outcomes O sub xy, where X goes from 1 to 100, Y goes from 1 to 4. So O sub 1, 2 is X equals 1, Y equals 2. So student 1 with teacher 2. In general, student X with teacher Y. And so if we wrote the probability X is X and Y is Y, then that's the probability of a student X being allotted to a teacher Y. The probability of that outcome. When we write probability with the 2 variables X and Y taking on values, we often call that the joint probability distribution of the X and Y variables. We often write it in a function form, P of xy.